fall. All right. The most important case of constant acceleration is something that we deal with all the time. It is the acceleration due to the force of gravity pulling us down to the center of the earth. That also affects things that we drop or throw. We can take our kinematics from earlier and add an up, down, or a y-dimensional spin on them. So what I've done is I've taken all of the positions as we typically understand them in the x dimension, and I've changed them to the positions in the y dimension. Lots of different conventions in here. The AP text tends to use the capital letter Y instead of the X for the Y position, and the X position is X. Now, when we deal with acceleration, we're not talking about any acceleration. We're really talking about the acceleration in the Y dimension, which is typically that gravity. And so you'll see when we combine them that we have the Y position is equal to the initial Y position plus the velocity times time plus 1/2 gravity times t squared, and so on and so forth. So you'll see the A substituted with G, and you'll see the X's substituted with Y. Don't let those mess you up. So when we are graphing position time graphs, usually we're in the lower fourth quadrant here, where you have positive t values but negative positional values. And when you see a curved effect on a position time graph, when you're talking about the y dimension, then typically that you're looking at an acceleration due to gravity. Now, this velocity is not constant, it's changing, and it's changing at a constant rate. That constant rate is 9.8 meters per second squared. So if we look at a velocity time graph in that lower quadrant where you're having negative velocities and positive times, this will get linearized, so we have a straight line, a constant acceleration due to the force of gravity. And so we take this acceleration, we're going to call it g. And we understand that gravity is always down. Now, I wrote negative 9.8 meters per second squared because right now I have a negative slope, and it makes sense to write that. When you're dealing with gravity, it's important to annotate the reference point. And there's a lot of different ways you can do this. Typically, we'll draw something like this, indicating that to the right and to the down are going to be positive. Now, gravity, the force of gravity is equal to the mass of some object times an acceleration. So this acceleration caused by Earth's gravity is always down to the center of the most massive thing. So anywhere on the planet that you are. Now, oftentimes when we do problems, we're dealing with a ground and a building. Sometimes we're dealing with like a cliff. And it's going to be important to understand which reference point you're going to use. Now, if you are dropping things down and everything is going to happen in this area, then it makes a lot of sense to call down positive. That makes acceleration down also 9.8 meters per second squared. So because acceleration of gravity is always down, and it's in line with your reference point, it becomes positive. And so when you stick it into your equations, you're always going to have positive numbers because you're always talking about things going down. Now, the other thing that this reference point does is that if you have an initial position and a final position, that this initial position is 0, and then that positive is going to be, or that second position, or that final position is going to be a positive number because it's all in line with the direction of your reference point. Sometimes we'll launch things. So if I talk about a rocket going into space, everything in this case is happening above the ground, and so it makes a little bit more sense to have a reference point that is up and to the right, that's positive. Now, acceleration due to gravity is still 9.8 meters per second squared down, and because that gravity is down and it's opposite of your reference point, this is now going to be negative. Now when you write your positions, this is still position 0, and this up here would be your final position, which would be a positive number because you're transitioning with your reference point. So your reference point becomes very important. Now if you have something complicated, like maybe you kind of combine these two aspects where I'm going to shoot a rocket off a building and then it's going to go below my origin point and hit the ground. What do? Do I have a positive up reference point or a positive down reference point? Really the choice is yours, it's just you got to keep track of everything. This rocket is going to launch with a certain velocity, and then when it comes back to this point, it's going to be impacting with that negative launch velocity. And so as it continues down into the ground, that impact velocity would be a negative value as well, because everything started here positive where you're going up and then you came down, all your velocities were down. Now if we did this type of thing, you would have a upwards positive reference point, which means that the acceleration is also going to be negative because you're going against the reference point. So it can get kind of muddled if you're not careful. You just got to keep in mind you need to annotate your reference point as we go forward, and then any vector going in the same direction as your reference point is going to be positive, whether you call that up or whether you call that down. Let's do an example. Standing on a 30-meter building and throwing a baseball straight up at 12 meters per second, how long would the ball be in the air? Let's set a reference point and draw a picture. So I have a picture here of a building, and on the edge of the building I throw a ball straight up. It's going to have this trajectory, this natural curve, and it's going to end up hitting the ground. This distance is 30 meters, and my initial velocity was 12 meters per second, and it's in line with my reference point, so it's going to be a positive 12 meters per second. Notice I've written in that the gravity in the y dimension is going to be negative 9.8 meters per second because it's opposite of my reference point. Now I'm going to talk about the long way to do it because it will explain two different versions of how to handle these problems. And then at the end I'll go through the shorter version of that. So the first thing that we're going to do is split this up into two sections. I'm going to treat the top part as if I'm standing on the ground and I launch something up and it's going to end up impacting the ground, where I have a velocity at the top of 0 and my launch velocity is the same as my impact velocity. The second part of this problem is going to be me launching an object straight down with a negative 12 meters per second velocity, and it's basically like a faster drop an object off a building. So when I find out the time of t up, t down, and then t fall, I can add those three times together and I'll get the total amount of time that'll be in the air. And then at the end I'll skip to the shorter version and I'll show you how it all works together. So I want to know how much time it took to get halfway, and I'm going to use and then use symmetry to add that exact same time on the way down. So I only need to solve for half of this problem. So v at the top, when an object changes direction, it actually has an instantaneous velocity of 0. I know that my initial velocity is in line with my reference point, and so that's going to be 12 meters per second. My acceleration is gravity, and it's opposite of my reference point, so that's going to be negative 9.8. And then t up is what I'm going to solve. So t up is going to be 1.22 seconds. So this right in here is going to be 1.22 seconds. That also means that's only t up to get to this point where v is equal to 0, because I used that in my equation. Well, this is going to be the exact same. So as this object slowed down at 9.8 meters per second for each second that it was in the air with a starting velocity of 12 meters per second, this is going to have a starting velocity of 0 meters per second, and it's going to increase in speed at 9.8 meters per second for the same number of seconds that it was in the air on the way up. So what comes up must go down at the exact same time. So this is actually t up and t down. Because this was launched at 12 meters per second, it gained some height. Now that it has more height, it has more energy, and then that energy is going to be put back into it as it falls. So even though it lost speed to get to 0, it's now going to gain speed to get to 12. So it's going to be the same velocity as when it launched, only it's going in a different direction. My change in position is going to go from 0 to 30. So I'm going to have a negative 30 meter change because I'm dipping below my origin. My initial velocity, because I'm starting with that negative 12 meters per second on the way down. My acceleration is still opposite, so I have negative 9.8 meters per second squared times t squared. Now, this may not be intuitive yet, but what we want to do is get this guy into the quadratic formula, and then we'll use that to solve. I'll give you a little review here. This is in the form of ax squared plus bx plus c, where negative b plus or minus the square root of b squared minus 4ac over 2a equal to 0. Go ahead and simplify. This ends up being our t fall. Okay, so 12 minus 27.055 divided by negative 9.8 will get you 1.536 seconds. So we have the t up, the t down, and the t fall. When you add those all up, you get a total time of 3.98 seconds. So your total air time was 4 seconds. Now, I'm going to show you an easy way to do that. So what I've done is I've cut right to the chase. Now if you recall, before we split this into part 1 and part 2, where part 1 I found t up and then I added both sides of that to get to this point right here. So total time from there to here, and then now I had a negative velocity on the way down for the rest of the 30 meters. You'll notice that here I'm going to use just the positive 12 and the same displacement and the same acceleration. Again, the only real difference that we're seeing here is this negative sign on the b variable. And when you do that math, choosing the minus sign because you can't have negative time, you end up with 3.99 seconds for total air time. So you can see, jumping right to this and using the existing initial velocity, you don't really need to break these up into two separate issues. Now, depending on what the question is asking, you may only need this portion, that first part of the math that I showed you, because you're on a level ground and you're launching a rocket and you want to know when it impacts the ground at the same origin. Or if you wanted to drop something off with an initial velocity of 0, or if you had an initial velocity of maybe negative 12, you could find this portion independently. This particular question, you were standing on a building, launching something straight up into the air, watching it fly and then fall past your origin to the ground. And in this particular instance, you can just use that initial velocity, and you can use the quadratic equation, and it will spit out pretty darn close to the total air time of that object.